I can't believe this is happening. We'll have 3 extremely exciting exercises in this episode, so stay tuned.
In the first exercise, Carolina will have to give us her first idea of what's on a picture. Carolina, please tell us your first thought that comes to your mind when you look at this picture, but the answer has to come fast.
Koala bear.
Okay, good, very good. Second picture.
It's a bat.
Okay, good. Next picture.
Clown.
Interesting, all right. Fourth picture.
2 dogs.
Beautiful. Next one.
It's a chicken.
Very good.
This one looks like a pelvis.
Looks like what?
Pelvis.
I don't even know what that is. Okay, fair enough.
Miednica.
Next one.
A clown.
Okay, good.
Exploding Coca-Cola bottle.
Beautiful. Okay, good job. In the second exercise, Carolina will have to group these items into random groups based on her own intuition. Okay, Carolina, come on over and start grouping them. Okay, but tell us what you're doing. Explain what you're doing. Okay, so Carolina received some data points, right, and different objects. And based on what she saw, different shade, different color, she could group these into 4 different groups. But now, what's going to happen if she receives new data that she never saw before? Okay, Carolina, here's a dark green cube. Where would you classify this one? Dark green. Okay, you had to put this one next to the other lighter green cubes because it has the same shape and similar color. Okay, but here's a curveball. What are you going to do with the cube that is blue? Are you going to place it in this group or in this group? So the color goes here, the shape goes here. Where are you going to put this cube? Okay, fair enough. That was your choice. But the real question is, was that correct? And we won't really know because based on these features, color and shape, we can't really tell for sure. Okay, one last item. A total curveball. I'm going to give you Zoe's sand tool, all right? A shovel for sand. Where would you classify this yellow shovel? You don't see a color, that's yellow, on the table. Neither do you see any shovels. So where are you going to put this? Oh, interesting. So you had put this in a different group. In this third exercise, Carolina will have to label the same pictures she did in the first exercise, but into 2 groups. The first group will be related to human beings, and the second group related to animals. So for each picture, Carolina has to say human, person, or animal. Okay, Carolina, first picture. Person or an animal?
Animal.
Good. Second picture.
Animal.
Good. Third picture.
Animal.
Wow.
Human.
Good.
Animal.
Good.
Animal.
Good.
Human.
Very good.
Human.
Okay, that was a tough one. And that's it. All right. So even though she described these pictures differently in the first exercise, now that I've made it simpler, I have told Carolina that there are only 2 options, 2 labels to describe these pictures, human versus animal. It was much easier for her to identify human or an animal next to each of these pictures. We can describe all these 3 different exercises as classification. Exercise number 1 was classifying each of the shapes based on Carolina's first thought. And we had so many different labels. Each picture had a different label, right? The second exercise, classification, we had put our objects into different groups. and then received new data, new objects, and try to classify them based on selected features, the color of the object and the shape of the object. And then going back to the third exercise, we had the same pictures as we did in the first exercise, but I had told Carolina that there are only two labels. Pictures that represent humans, people, and the second group is representing animals. And then Carolina had an easier task, because all she had to do was use those two labels to describe the photos. Now, all of these examples we call classification.
First, let's take a look at the structure of a classification dataset. Classification datasets will have the following variables used later in the model. 1. Independent variables called features. These variables should be uncorrelated and represent unique features of our observation. 2. A dependent variable called the label that we'll be predicting using our models. It's the outcome variable. Let's take a look at a data frame in which we are trying to classify animals into two groups, birds and mammals. We are given three features: body weight, body length, and body width, and the label for each observation. We have two birds that are lighter, looking at the weight, shorter and narrower than the two mammals in our data. Based on our three features, weight, length, and width, we can classify new animals into our two labels. Since a pigeon and the eagle are lighter, shorter, and narrower than the other animals, we classify them as birds. The cat and the dog are heavier and bigger than the other animals, so we'll classify them as mammals. What I want to do now with you in RStudio is to create the same data frame with our features and labels, independent variables and dependent variables, before we take it further into our predictive modeling. So let's create the same data frame with animals, with features such as weight, height, and width, and the label being either a bird or a mammal class. In RStudio, I'll open up a new script right here in the upper left-hand corner, and we're going to create our features first. So the first feature is weight, and I'll create a vector for the weight, for the height, and the width, and then put them together in a data frame. Let's start with weight. Weight, reverse arrow, and then the C function. In the C function, I'm gonna take the same data points as we did previously. So 30, 25, 150, and 300. 30, 25, 150, and 300. Okay, for animals, right? Command return. It went to our environment numerical vector 30, 25, 150, 300 for elements. Okay, now the length of my animal. Going back to our table, we had 120, 130, 520, 480. 120, 130, and I forgot what the next one is. 520, 480. 520, 520, and 480. Okay, and the third feature was width. Again, reverse arrow in the C function. And in the width, we had 70, 82, 70, 82. Then we had 170, 195. 170, 195. Okay, good. And I submit all of these three vectors to my environment. Okay, I have my features. Now, my labels. What we had said in the previous video is that the first two animals are birds. They are simply lighter right? 30 units and 25 units, lighter compared to the other two animals. They are also shorter, 120 and 130 compared to 520 and 480. So our birds are shorter. And the width, 70 and 82, which means that they are narrower than the other two animals, 170, 195, right? Okay. And the other animals, in our case, are mammals. They are heavier, 150, 300. They are longer, 520, 480. And they are wider, 170, 195. Makes sense. Birds are smaller than mammals. Mammals are bigger. Pretty straightforward. Good. So now I'll create my features. And I'm going to call this, so I created my features. I'm going to create labels. Labels. I should not use the labels because labels is a function in R. So let's use something else. How about classes? Reverse arrow. And then I'm going to say double quotes bird. Double quotes bird, because the first two are birds, right? Then mammal, and the fourth one is a mammal. Okay, good. So now what I can do is combine all these four vectors, 3 that are numeric, my features, and 1 that is a character, could be converted to a factor, right? Bird, the bird level would have a number 1, and the mammal level would have number 2, right? And I can convert my classes to a factor. All right. So let's combine all 4 vectors into one data frame. I'm going to call it my underscore data underscore frame. Reverse arrow. And I'm going to do a cbind. I'm going to bind by the column. So previously, in episodes 2 and 3, we did a row bind like this, union. But now what we want to do is a cbind. We're going to combine columns. We're going to combine variables. Cbind. Cbind, weight, length, and width, and classes. Okay, good. Command return. We got a data frame, four observations, 4 variables, and if I double click on this, it'll give me my weight, my length, my width, and my classes, exactly as the data frame that we discussed in our small cartoon video. To make the next part of this video more exciting, I'm going to add more animals to our simple data frame. If I go to the weight vector, I'm going to add 2 more animals, 1 bird and 1 mammal. So the bird, comma, I'm going to say the bird is a little bit heavier. Let's give it 45 units of weight. And the mammal will be also a little bit heavier. Let's give it 320 units of weight. All right. Now, in terms of length, I'm going to add, so the bird is bigger. I'm going to add 1 more bird. Let's say it's going to be 140 units of length. And our mammal is bigger as well. Let's make it 540 units of length. Same thing with width. With width, I'm going to add a bird that is a little bit wider. Let's say 90 units of width. And the mammal will have 200 units of width. All right. And for our classes, we have to add 2 more elements, a bird and a mammal. Good. So I am going to rerun my code, command return, and pop up the data frame. Okay, so now I have 6 animals. 2 birds, 2 mammals, 1 bird, 1 mammal. All right, the last 2 are a little bit bigger in their classes. Right? But the same holds, the bird is still smaller than the mammal. And a few more mainstream classification examples. The first example is going to be classifying objects on a photo, on a picture. And you've probably seen a lot of self-driving cars, autonomous cars, Lyft, Uber, all those companies are going into self-driving cars. And in this case, what we will do is we will actually try to find cars on our photos, right? So here's the first example. This is my car. Guess what? If you put this photo into a package that does object recognition, then it's going to see that in this picture, you'll see at least 2 cars. Well, I can say as a human being more than 3 cars, right? But the algorithm classified 2 objects as cars. My car in the front view, and 1 more car, my neighbor's car in the garage, right? And then moving on to the next example, same car, but from a different angle. The algorithm has seen so many different cars that it can identify a car from different angles, perspectives. Okay, so in this case, it was able to identify my car from the front view and from a back view, the trunk view. Another example of classification, a mainstream example would be handwriting. I have actually handwritten a few digits here from 1 to 8. Actually, I skipped the number 2, but I have 1, 3, 5, 6, 7, 4, and 8. And what really happens here, without going into too many details, because we will not focus on this, what happens is every single digit will be put on a grid, on a matrix, okay? And these small squares in this matrix will be either black or white. Black if the handwriting went through that small square, or white if the handwriting did not go through that square. So for a human being, it's extremely easy to identify handwriting. We know this is number 1, this is number 5, number 7, number 3, 6, 4, and 8. For a computer, it's a little bit different. A computer will need to get enough handwritten number 1s to be able to identify different angles between this and this leg. It'll have to accommodate for different thickness of these lines. So the computer will have to get a lot of data, a lot of handwritten 1s, to be able to actually recognize if this is a 1. Number 1, 2 distinct movements, right? Up and down, okay? Number 7, very similar. So again, the question would be, how would the computer know, how would the algorithm know the difference between these 2? How would the computer be able to classify 1 as 1 and 7 as 7? Sometimes the computer would misclassify number 7 and say that it's number 1. Or sometimes it would misclassify number 4 and say this is number 7. This is actually a very common error in handwriting. So we've seen a few examples of mainstream classification, right? But what we want to do now is take what we've learned based on these examples, how the training data is important to train our data set, and then train our model to be better at distinguishing different patterns and telling us that number 7 is 7, number 4 is number 4, right? We also seen how to classify pictures, right? But now the real question is, can we take this knowledge and apply it to a data frame, right? In this case, maybe the German Quarter data frame that we were using in class, right? Or simply put, is there a way for us to learn how to select the data for training, okay? And then maybe selecting a good sample of data for testing our algorithm.
Before building any predictive models, we should make sure that we have the following data sets that have the same structure but different observations. 1, the training data set that we'll use to build our model. And 2, the testing data frame that we'll use to test the model is good. The testing data was not previously seen by the model. It represents new or future data. We typically get one data set, and we have to split that data set into 2, training and testing, called samples. We can split our population data set into 2 sample data sets using the following techniques: random sampling or stratified sampling. Random sampling selects the sample observations at random. We have very little control over which observations are selected, making them more realistic. Random sampling is great for data sets that have homogeneous observations.
Random sampling. Now that you know what random sampling is, simple random sampling, we can try to code it in R. What we're going to use is the sample function, very well known, sample. What I will do is I will sample indices from my data frame. the row indices, the observation indices. In our case, we have 6 observations, 6 animals, right? 3 birds and 3 mammals. So I will sample from an index from 1 to 6 for my training and my testing data, right? So what I'm going to do is I'm going to sample function, sample, parentheses, sample from 1 through 6. Okay, I'm going to sample from the row index of my data frame. In other words, I could say 1 through n row of my underscore data underscore frame. Same thing, right? N row. I'm going to get a vector from 1 to 6 in my console. 1, 2, 3, 4, 5, and 6. Good. Now, sample size. How big should my training data be? How big should my testing data be? There is usually a 80-20 rule of thumb. So 80% goes to training, 20% goes to testing, and of course this depends on how big your data set is, how accurate you want the training to be, and how accurate you want the testing to be, etc., etc. We will actually use 4 out of those 6 observations for training and 2 observations for testing. So in my sample function, I need to define the size of my sample. Size equals 4, right? 4. And I will save this in a object called training underscore index. Training underscore index, reverse arrow, sample from a vector of 1 through 6, where the size of my sample is 4. So I'm going to select 4 indices, row indices, from my data frame. Okay, so if I run this line of code, what I will get is the training index. So my random sampling, I just sampled randomly with the sample function, right? So my random sample has the following 4 indices: 2, 6, 3, and 4. Okay, the random sample for my training data selected observation number 2, observation number 6, observation number 3, and observation number 4. Okay, good. So now, what I'm going to do is I'm going to use this random sampled index, 2, 6, 3, and 4, to pull the data out of my data frame. Okay, so what I will do is I will say this: training underscore data frame, reverse arrow, okay? And I will want the data from my underscore data underscore frame, squared brackets, comma, and in the row index on the left-hand side of my comma, I'm going to say training underscore index. And I want all the columns, so I'm going to keep the column index empty. Command return. Beautiful. So what I get in return in my training data frame is the data for the 2nd, 6th, 3rd, and 4th animal, right? So we have 1 bird and 3 mammals. Good. Now, this is my training data frame. I also want to build my testing underscore data frame. Reverse arrow. My underscore data underscore frame. Comma, same thing. But now I want to exclude my training index. I want to exclude from my underscore data underscore frame, exclude indices 2, 6, 3, 4, and leave the remaining indices. To do that, I'm going to use the negative training underscore index. The negative will exclude these indices from my observations. So let's run this. And the testing underscore data frame has 2 observations and 4 variables. So let's double check this one. And I got the 2 birds that are missing from the training data frame. Okay, good. So this is exactly how I create my training data frame and my testing data frame using random sampling. The random sample, 4 observations. The testing sample, 2 observations. Here is my training data frame with 1 bird and 3 mammals, and my testing data frame with 2 birds.
On the other hand, stratified sampling ensures that each subgroup of a given population is adequately represented within the samples. Let's say that we have 2 birds and 2 mammals. Our stratified sampling will select 1 bird and 1 mammal, giving it a 50-50 split, 50% birds, 50% mammals, just like in our population data frame.
What we had noticed before is that we have 2 data frames, right? The training and testing, in which the training had 3 mammals and 1 bird. Let's quickly pop it up. 1 bird and 3 mammals in our training data set. Does this mean that our model won't see the other birds?
That's correct. Does this mean that the model will miss something from the birds population? Probably yes. This training data frame, the problem is with this training data frame is that it's unbalanced. It doesn't have a good enough size of the bird population. It has a lot of mammals, but only one bird, and that's a problem because we had more birds, right? And we're missing some information. On the other side, the testing data frame had 2 birds and no mammals. Does this mean that my model will not get tested for the mammals? That's right. So I just pointed out 2 problems with our random sampled training and testing data frames. The first one is that the training data set does not have enough bird information, hence it won't capture all the features that are necessary. On the other side, our testing data frame doesn't have a mammal, so we won't be able to test our model for a new mammal. There is a solution to these problems, and the solution is stratified sampling. We will pinpoint our sampling function to a variable, to the labels, so that it knows that the training and testing data frames should have the same proportion of birds and mammals as the population. So let's go back to our R script, and let's install a package. Install.packages, parentheses, double quotes, split stack shape. The package name is called split stack shape. Command return, I'm going to install. Okay, so it's installing, it's hitting my CRAN, it's downloading some files, and now downloaded binary packages are in this location. So now library, statement, and split stack shape. So what I'll use now is a function called stratified. And if I should take a look at the help box here, the stratified function samples from a data frame in which one or more columns can be used as grouping variables. Exactly what we need, all right? So I am going to use my underscore data underscore frame for this stratified function, but I will have to use the as.data.frame function to force this data frame to be a true data frame object, so that my stratified function doesn't get confused. So as.data.frame and my underscore data underscore frame. Good. Comma. Now I want to provide the group argument. The group argument will tell the function which variable to use to do the stratas. The group argument needs a numerical index of the variable it needs to use. In our case, it's the 4th variable, right? If I pop up my underscore data underscore frame, 1, 2, 3, 4, my labels are in the 4th variable. So I'm going to say group equals 4, comma, sample size. And here it's best to use a decimal that represents the portion of my data used for this stratified sample. Let's use 60% of our data. Let's use 60% of our data for the training data set. And now if I say command return, it'll give me a beautiful data frame in my console with all of my 4 variables and all of my 4 observations, 4 animals for my training data set. Okay, I have 2 birds and 2 mammals, so my sample is well balanced. My training sample has 2 birds and 2 mammals, 50-50. The same proportion that was in my underscore data underscore frame, the native data. I am using the same proportions for all of my samples, for all of my training and testing data frames. Okay, so I'm going to save this function in a new object called strat underscore train reverse arrow, and then the stratified function with size equals 60%. Okay, so now if I run this, we'll get our new data frame. What we have right now is a training data set. Great. 4 observations. But you might be asking what to do to get the testing data set, right? We have the training, but we also need the testing data set with the remaining 2 observations. Well, this function actually has a built-in argument. So if I copy this function and paste it below, I can add an argument called both sets.
logical. Should both the sampled and non-sampled sets be returned as a list? The answer is yes, true. So both sets equals true. Okay, and now if I run this function with the both sets equals true argument, we will get a list of 2 data frames. One data frame, our training data frame, I am looking at my console at this point. One data frame, sample number 1, with 2 birds and 2 mammals, 50-50, the same proportion as we had in our population data frame. And we get the remaining 2 animals, 2 observations, 1 mammal and 1 bird. So totals, we have 3 mammals and 3 birds, makes sense. Both samples, training and testing, have a 50-50 proportion of birds and mammals. Great. So our training data set is well balanced and our testing data set is well balanced. So we can save this outcome in a new object called training underscore testing, reverse arrow, and then the stratified function. If we save this in the training underscore testing object, we'll get a list of 2 data frames. So I can call the first one training underscore testing $sample1 for my training, right? So comment, this is my training data. And the second one, testing. So same list, training underscore testing list, $sample2. This is my testing data. Oh, this should be a hashtag. Great. So now if I run each of them individually, I'll get the individual sampled data frames, my training and testing separately.